March 1945 captured American Ordnance Depot, outskirts of Remagen, Germany. Smoke drifted through the rafters of a half-bombed warehouse as German officers stepped carefully among piles of enemy ammunition. Broken crates spilled rifle rounds across the floor, gleaming oddly pale in the thin light. Major Friedrich Keller, an engineer from the Waffenamt, Germany's armament office, picked one up. It felt wrong. Too light. The cartridge clicked softly when he tapped it against his palm. He slid it open with a folding knife. Instead of the familiar yellow brass glint, he saw a dull amber sheen. The edge flaked under the blade. Plastic. He stared, disbelieving. A murmur passed through the inspection team. "Impossible," someone said. It would melt. Keller said nothing. Beyond the shattered door, distant artillery rumbled, an army molded from steel listening to its own funeral. Inside, they turned the cartridge over again and again, weighing not just a bullet but the idea behind it. In that moment, the Reich's myth of mechanical superiority fractured. While Germany had spent years perfecting metal and machine, its enemy had done something unreal, replaced industry's lifeblood with chemistry. The Americans were now casting weapons from materials the Germans considered toys. From that small translucent shell, they saw the future and understood, too late, that they had been out-invented on an elemental level. At the opening of the Second World War, every major power entered the conflict believing victory would depend on metal. Steel-built tanks, brass-fed machine guns, and aluminum filled the air with fighters. The German war machine embodied that creed perfectly. Heavy, precise, and industrially pure. In Berlin's factories, engineers treated metallurgy as art. Chemistry was considered auxiliary, useful for fuels and coatings perhaps, but hardly equal to iron or copper. Across the Atlantic, America prepared for war differently. The United States had resources, yes, but it also possessed an industrial diversity, unmatched anywhere on Earth. Its factories turned out cars, telephones, machine tools, and plastic. By 1939, the word itself still sounded experimental, closer to novelty than necessity. But in research labs at DuPont, Eastman, and Union Carbide, polymer science was quietly maturing. Even before Pearl Harbor, Washington understood what global conflict demanded: mass production under scarcity. When German U-boats began tightening their stranglehold on Atlantic shipping, U.S. economists saw a dangerous pattern emerging: copper and brass stocks dwindling faster than ships could replace them. Ammunition orders outpaced mining 10-1. Every cartridge case, every shell fuse drew from the same limited pool of materials feeding power grids and factories. The nightmare was simple: winning battles but losing resources. In mid-1940, President Roosevelt formed the National Defense Research Committee, NDRC, calling together an unlikely army of chemists, physicists, and industrialists. Their directive was unambiguous: keep American armament lines immune from shortage. Among their many contracts sat a line that would later baffle the remnants of the German Ordnance Office: Project Lightweight Ammunition, study of substitute materials for cartridge casings. Within months, researchers at Frankfurt Arsenal in Philadelphia began testing combinations of cellulose acetate, phenolic resins, and nylon, names more familiar to toy manufacturers than soldiers. Each compound faced the same question: could plastic survive the chamber pressures of modern firearms? Results hinted at possibilities. Early polymer casings deformed under extreme heat but bounced back instead of splitting. They were nearly half the weight of brass and completely immune to the corrosion-plaguing ammunition stored in tropical climates or damp cargo holds. By the time Japanese bombers struck Pearl Harbor, the U.S. had already woven chemistry into strategy. Plastics would become the hidden skeleton beneath the nation's war economy. Not just in bullets, but in radios, canteens, aircraft canopies, and electrical insulation. Every field where metal could be saved, plastic advanced. It wasn't glamorous. It was pragmatic. American engineers found themselves moving from drafting tables to laboratories, their hands smelling not of oil and polish, but of acetone and resin. The Arsenal's chemistry division wrote quietly prophetic words in an internal memo: there will come a time when war will be fought not only with iron and powder, but with molecules themselves. While across the Atlantic, Germany's engineers, burdened by years of metallurgical doctrine, ignored the shift completely. They still trusted the same alloys that had armed the Kaiser, even as Allied blockades tightened and material shortages mounted. Changing the philosophy of war production seemed sacrilege. By 1942, the contrast between the combatants extended beyond factories. It was cultural. The Reich equated craftsmanship with purity. The United States equated plasticity with survival. Their battle would soon prove that adaptation, not tradition, defined the industrial battlefield. In the laboratories of Philadelphia and Delaware, vats of newly mixed polymer waited to be shaped into weapons. Across occupied Europe, German scientists would not glimpse those creations until too late, when fragments of translucent casings littered captured battlefields, whispering of a chemistry they had dismissed as fiction. From that divide, a new kind of weapon began to take shape, one that couldn't rust, couldn't deform, and, to the astonishment of the old engineering world, could be poured rather than forged. By 1942, American production lines were transforming at a pace that stunned even military planners. Factories that once stamped automobile panels or molded kitchenware now hummed with the rhythm of total war. In Detroit, rubber machines spun out synthetic compounds for seals and gaskets. In Rochester, chemists at Eastman blended new formulae of cellulose and acetate. In Wilmington, DuPont engineers mixed batches of polyester and nylon strong enough to replace silk, even steel in certain tolerances. The motto spreading through the U.S. industrial corridors became simple: if it's rare, replicate it. The metal crisis prompted the U.S. Ordnance Department to invest directly in the impossible idea, a bullet that didn't need brass. At the Frankfurt Arsenal, the country's oldest ammunition plant, engineers tested case molds made of phenolic resins fused under pressure. Each new pattern was fired, measured, shattered, noted, refined. The data they collected formed the secret core of Project Lightweight Ammunition, where polymer casings were evaluated for small-caliber weapons like the .30-06 Springfield, the .45 ACP, and later the M1 carbine. The first successful trials startled traditionalists. Cartridges produced in batches of pressed resin didn't burst under standard chamber load. They burned at consistent pressures and ejected cleanly. Soldiers handling test lots found them shockingly light, saving nearly 15 kilograms of weight per 1,000 rounds. In jungle or Arctic conditions, they resisted corrosion better than brass-cased shells. Engineers realized plastics had quietly become a logistical weapon of their own. Outside the laboratory, the chemistry revolution was spreading across the arsenal. Newly invented plexiglass replaced aluminum in aircraft canopies. Bakelite substituted steel in control knobs and fuse housings. Radios carried miniature plastic gears. Paratroopers wore nylon cords and polymer buckles. Synthetic substitutes were no longer experimental. They were the literal fabric of the American war. German military intelligence first heard rumors of these tests through intercepted trade, journals, and scattered after-action fragments. Reports filed to the Heereswaffenamt mocked the notion as Allied desperation. American industry seeks to fire weapons made of toys, one colonel scribbled beside a captured manual. But the arrogance soon cracked. On the Italian front in late 1943, Wehrmacht engineers examining captured U.S. ammunition encountered something bewildering: a rifle casing molded from resin, marked with American ordnance stamps. Field tests contradicted all expectation. The plastic case fired flawlessly. The officer's report from that inspection simply read, "Unmöglich und doch vorhanden." Impossible. And yet it exists. That discovery triggered curiosity shaded with disbelief within Germany's scientific elite. For 2 decades, they had equated progress with superior metallurgy: chrome steel, tungsten, high-grade alloys. Now, staring at the byproduct of American chemistry, they confronted a philosophical defeat. The enemy was not just outproducing them. It was inventing entirely new materials faster than the Reich could mine the old ones. Even before Berlin's laboratories organized a comparative response, the flow of Allied innovation was outpacing intelligence. Nylon hoses replaced cotton cloth in American trucks. Synthetic glue sealed aircraft panels. Lightweight polymers insulated every new radar set crawling overseas. None of these items bore a blade or barrel, yet together they redefined what logistics meant amid global war. By 1944, the plastic bullet program symbolized the United States' underlying wartime doctrine: flexibility through science. While Germany's engineers were trapped perfecting machines like the Tiger tank, America's were redrawing the boundaries of matter itself. The two philosophies would meet not on a battlefield, but in the stunned expression of German technicians combing Allied depots in the war's final months, realizing that even the smallest thing, a cartridge case, had rendered their industrial discipline obsolete. From this cultural collision emerged a new question that would linger long after the shooting stopped. If the future of warfare could be molded by hand, what else, in time, could be made unbreakable? The chemistry behind the American plastic bullet represented more than an improvisation of wartime scarcity. It marked a transition from mechanical engineering to molecular engineering. The scientists at Frankfurt Arsenal, aided by civilian specialists from DuPont and Union Carbide, took the same polymer technology used in telephone housings and shaped it to meet the punishing physics of ballistics. Every test began with heat and pressure measurements nearly 50,000 pounds per square inch inside a rifle chamber. Plastic had no right to survive that. Yet by altering the polymer chain with powdered glass, cellulose, and phenolic resin, they created casings that softened briefly under heat and rehardened immediately when ejected, flexible where metal was brittle. The ammunition not only saved copper and brass, it revolutionized handling. In freezing weather, polymer didn't seize. In salt air, it didn't corrode. Chemists soon realized they could color-code batches to identify loads instantly. Red for tracer, yellow for blank, green for training rounds. The material itself carried intelligence. For Germany, whose factories relied on intricate machining and scarce alloys, the discovery defied accepted logic. Plastic was for knobs and headphones, not for weapons. But America's polymer casings proved that innovation was not about perfection, it was about adaptation. A machine could be elegant, a material could be strategic. The flying fortress or the atomic bomb defined scale. This small translucent shell defined direction, the age of molded war. American power during the war rested less on genius than on rhythm, the ability to turn theory into production overnight. The War Production Board operated networks of subcontractors, assigning research projects to ordinary manufacturers of combs, buttons, and insulation. Those same presses that once stamped dinnerware now pressed ordnance. Plastic pellets replaced brass billets, and factories learned to pour their output instead of forge it. At Remington's Bridgeport plant, injection molding machines ran 24 hours a day manufacturing experimental phenolic cartridge tubes. Every rejected batch revealed new formulas for resilience or failure. Chemists cross-referenced results with munitions engineers, and the process repeated until success occurred as predictably as an assembly line. The benefits rippled outward. Lighter ammunition meant more rounds per crate, faster loading, cheaper shipping. For the quartermasters supplying the Pacific Theater, weight translated directly to fuel, less cargo tonnage for the same firepower. The Army calculated that large-scale adoption could have cut shipping loads by tens of thousands of tons over a year. Even when production never reached mass issue, the experiment reshaped manufacturing philosophy itself. America had proven that chemistry could substitute metallurgy, and that every boundary between civilian and military industry could disappear overnight. In that synergy lay the true weapon of the United States, not a bullet that killed, but an economy that learned. Behind the quiet experiment stood a fraternity of scientists unused to uniforms, men and women like Dr. Herman Mark, a Viennese refugee who brought deep polymer knowledge from pre-war Europe, and Wallace Carruthers' successors at DuPont, who transformed laboratory nylon into structural strength. Their white coats replaced the soldiers' combat gear, yet they understood the urgency as intimately as those on the front lines. Each breakthrough in polymer chemistry had immediate military application: nylon for parachutes, plexiglass for bomber canopies, polyethylene for radar insulation. Wartime funding boosted research by decades. For the first time, the United States fused its scientific elite directly into command structure. Physics and chemistry became branches of strategy. These scientists recognized that the polymer revolution's principle was mobility itself. Materials could be altered to fit any purpose, stiffened into casings, softened into seals, spun into fibers. Militarily, it meant America could manufacture resilience. Philosophically, it meant a new kind of warfare. One fought not only with armies and factories, but with the plasticity of imagination. The German emphasis on perfection by tolerance and calibration belonged to an age of micrometers and lathes. America's age was molded in vats and kilns. The two conceptions of science, precise versus adaptive, met in the middle of the 20th century under the harshest possible test, and the Americans' proof of concept came out of a rifle barrel intact. Each of these angles, technological, industrial, and scientific, described the same metamorphosis: war redesigned at the molecular level. For the enemy, this was a revelation that steel minds could not suppress. But their astonishment would only deepen as they studied how these materials behaved under combat conditions, and learned that even defeat could be measured in grams rather than tons. Inside the surviving sectors of the German armaments bureaucracy, news of America's synthetic bullet filtered in as field rumors long before physical proof arrived. The first intact samples reached the Heereswaffenamt in late 1944, captured near Bastogne. Their lab technicians sliced the casings apart and stared in disbelief. The edges melted slightly beneath magnifying glass heat, proof of an organic compound. Reports flashed back to Berlin describing a composition resembling cellulose combined with unknown binder. Some dismissed it as propaganda, a trick, a training dummy. But the results of firing tests silenced doubt. The casing withstood chamber pressure, and the weapon fired normally. The astonishment was more philosophical than practical. To German engineers raised on notions of rigidity and precision handcraft, the idea of molding, not machining a component, felt like heresy. They had equated quality with weight and reinforcement. America equated quality with efficiency. By 1945, Germany's own plastics research had withered under shortage. Phenolic resins existed, but mass molding required power and petroleum they no longer possessed. The weapon that most unsettled them was not shaped by superior firepower, but by abundance of imagination. The Reich had invested in miracle metals. The United States had invested in flexible minds. And in that inversion, every German engineer glimpsed how the war had already been lost long before their machines stopped running. In the field, these innovations merged quietly into daily logistics. Polymer casings never became standard issue, but the design philosophies that birthed them saturated the Allied supply chain. Radio operators handled circuit boards encased in resin. Artillerymen loaded shells packaged in synthetic fiber sleeves. Navy gunners fired tracer rounds sealed in moisture-proof plastic tips. Infantrymen who carried early test lots noticed subtler differences. Ammunition pouches lighter by several pounds, weapons less prone to jamming in rain or sand, rounds immune to the green corrosion that plagued brass under Pacific humidity. Pilots over Burma and New Guinea appreciated the innovation without even knowing it. Aircraft wiring insulated by polyethylene never short-circuited under tropical heat. Meanwhile, enemy soldiers collecting debris from these battlefields unknowingly handled artifacts of chemistry's conquest. They found shards that didn't rust, that snapped when pressed yet outlived the battlefield itself. In their reports, officers classified the material as unknown compound, unmetallic, difficult to categorize. The future had literally broken apart in their hands. Everywhere the Allies fought, they carried proof that flexibility was might, that a supply line could stay mobile if its elements refused to rot, rust, or crumble. For American soldiers slogging across oceans and continents, this invisible revolution mattered as much as any tank or aircraft, the quiet endurance of materials shaped for conditions rather than tradition. When post-war analysts revisited the polymer experiments, they realized the plastic bullet was less about the cartridge than the concept. It symbolized a civilization retooling its understanding of permanence. Metal is finite, chemistry is infinite. In war, that shift had moral weight. The weapon that horrified German engineers represented one of the war's strangest ironies: progress born of destruction. The same polymer research that saved copper for bullets also gave rise to the materials that would later build peace. Fiberglass boats, nylon clothing, acrylic glass for homes. Military necessity had accelerated the age of convenience. Wartime chemists such as Herman Mark and Caroline Hunter later confessed a mix of pride and discomfort. They had proven that anything could be remade if one simply changed the elements, yet the first proof had come through weaponry. As one researcher wrote in 1946, "We learned too late that every molecule carries memory, either of war or of rebuilding." German scientists studying captured American plastics experienced a different reckoning. They saw that creativity, untethered from ideology, could reshape reality faster than the state could command it. Their laboratories in the post-war years would quietly adopt the same ethos, birthing polymer industries that defined West Germany's recovery. Plastic, once a symbol of inferiority, had humbled the master craftsmen of Europe and signaled the modern world's most enduring paradox. Our genius for invention owes as much to what we wish to destroy as to what we hope to build. From those translucent casings scattered across the battlefields of 1945 grew the unbreakable lesson that adaptability, not perfection, wins wars. The climax of that lesson would come when both nations, now at peace, faced the full measure of what chemistry had unleashed, a future molded for better or worse by the same plastic that once filled rifle magazines. Spring 1944, Frankfurt Arsenal, Philadelphia. The war in Europe was shifting, and inside a red brick laboratory on the Delaware River, test technicians prepared for what seemed the smallest yet strangest experiment of the conflict. On a heavy wooden bench sat a single M1 carbine, a chronograph rigged behind it, and a technician adjusting the chamber gauge. Beside him, under warm yellow lamplight, lay 10 cartridges, opaque amber in color, molded smooth as glass. Each weighed barely half of their brass counterparts. At the signal, the shooter raised the weapon and squeezed the trigger. The first report cracked across the range, a clean echo with no sign of rupture. The case ejected whole, only slightly scorched at the rim. The observers exchanged glances. Again and again the rifle spat plastic and fire, and each time the resin shell fell intact onto the floor. When the final round was fired, the range officer walked forward, picked one up with gloved fingers, and smiled. "It held," he murmured. The next day, telegrams left the arsenal for Washington. The design had proven stable under full pressure. The internal notes wrote it clinically. Phenolic casing, Series X113, functional for 10 consecutive firings. Recommend field evaluation. The report's lead engineer, Dr. Harold Booth, knew the implication. It proved that chemistry had achieved parity with engineering. At the same hour across the Atlantic, in occupied France, German field inspectors were writing inverse sentences, reports filled with dread rather than excitement. They had recovered fragments from Allied supply dumps abandoned in the Rush inland. Mixed among soot and brass casings were the brittle halves of a polymer cartridge. It made no sense. The sample showed carbon structure, not zinc alloy. The ordnance team cataloged it as munition experimentellum typus, believing it a rare prototype. In fact, they were witnessing the future. That spring marked a turning point in perception. Until then, Germany had viewed America's industrial might as numerical. Endless tanks, trucks, and airframes. Now it confronted intellectual mass production, the ability to innovate at a pace no laboratory hierarchy could duplicate. At the Heereswaffenamt, engineers requested new tooling to copy the idea. Their chemists, still mourning the loss of petroleum reserves and factory power, could only shake their heads. They lacked the basic resins to begin. From within their collapsing empire, German scientists glimpsed a truth more chilling than Allied firepower. They were no longer competing in the same field. The Americans weren't merely winning with quantity. They had altered the material definition of war itself. Even Allied officers who read the Frankfurt Arsenal Bulletin underestimated its symbolism. The plastic bullet remained largely experimental and saw limited distribution. Yet its success symbolized the unprecedented marriage of science and warfare. For the first time, the weapons of war did not trickle from blacksmith forges or turret lathes. They grew from chemical bonds. Had the war extended another year, ordnance analysts predicted that more than half of American small arms ammunition components might have become polymer-based. Factories were already designing automated presses capable of molding casings by the millions. In that moment, the world of copper and brass gasped at a smaller, lighter rival rising out of beakers and heat baths. The future of manufacturing was no longer smelted, it was synthesized. The people in that Frankfurt laboratory perhaps didn't sense they had shifted history. They only noted pressures, recoil, stress strain graphs. Yet outside those walls, the strategic meaning echoed all the way to Berlin. In a war about resources, the side that could invent new materials had achieved an advantage stronger than armor. Within months, the echoes of those gunshots would reach captured German armories, set off alarms through intelligence channels, and shake fundamental assumptions about what could and could not exist inside the barrel of a gun. What those astonished engineers discovered during the final weeks of the war, when they pried open Allied crates and stared at bullets cast from chemistry, would confirm every nightmare they had begun to suspect. April 1945, Ruhr-Valley, Germany. Coal dust clung to every wall of the underground chamber, where a team of German ordnance officers stood bent over the table. Between them lay the objects recovered from an overrun American supply train: cracked resin fragments, the spent tail of a cartridge, and one intact translucent round placed reverently on a velvet pad. The engineers who had spent their careers measuring microns of tolerance stared as if at an alien artifact. Chief Inspector Dr. Ernst Ziegler, an expert in metallurgy, tapped the item twice with the nib of his pen. He expected the brittle snap of failure. Instead, the cartridge gave a hollow tone intact. He turned it in the light, observing the faint swirl marks of an injection mold, creation, not machining, visibly seamless. He whispered almost to himself, "They have replaced the forge." Outside the bunker, artillery thundered. The Allies were within miles. Yet inside, the scientists' silence said more than the war outside ever could. Notes from the session survived the occupation. Composition unknown. Resistance to blast beyond expectations. Likely polymer of high heat tolerance. Test replication impossible under current shortage of raw materials. Those few technical sentences marked a realization heavier than defeat. In Berlin's collapsing war ministries, engineers confronted proof that German engineering supremacy had been overtaken by a new philosophy itself: chemistry as architecture. America's industrial miracle was not simply that it produced more, but that it reimagined matter altogether. Across the ocean, the same victory was being documented at Frankfurt Arsenal's experimental reports. Lightweight casing project terminated. Results to inform post-war ordnance standards. The phrase was bureaucratic, almost indifferent, masking the revolution beneath it. Captured copies of those files would circulate among Allied intelligence, their technical language translated, reprinted, and finally read by the same scientists who once doubted plastic's strength. What they held in their hands was both simple and incomprehensible. The most ordinary symbol of technological dominance the world had ever seen. A cartridge built from what their textbook still called a substitute. In the days following Germany's surrender, at American-controlled research centers in France and the Netherlands, German prisoners of science, materials experts, chemists, designers, stood before tables lined with examples of Allied polymer ordnance. They weighed them carefully, scratched the edges with their fingernails, and tried to reconcile how such fragility had endured combat. One later wrote in a private notebook seized after his repatriation, "These weapons tell us that the Americans have conquered simplicity. We believed in perfection. They believed in application. We sought purity of steel and lost the war." That entry was signed simply H. Wolf, 1945. The significance of that shattered belief extended beyond the workshop. For the United States, the success of polymer casings and components confirmed an ideology that would define the second half of the 20th century. The notion that progress depended not on the material itself, but on the ability to invent new ones. Chemistry had become strategy. By the time reports reached Germany's few surviving academic laboratories, the symbol had already transcended utility. The plastic bullet stood for every Allied innovation that proved the Reich's obsession with precision had become its weakness. The war's end cataloged an uncomfortable equation. Imagination multiplied by resources yields supremacy, even in fragments. That spring, as the American flag rose over ruined Rhineland factories, German engineers evacuated eastward carrying only notebooks. Inside them were sketches not of tanks or jets, but of polymer experiments hastily begun in imitation of what they had seen too late. Their future research would birth West Germany's chemical renaissance, but in 1945 those notebooks read as epitaphs. The final irony lingered inside one interrogated engineer's report to Allied intelligence. It was not the atomic bomb that frightened us most, but your plastics. It meant you could build anything, anywhere, from nothing we understood. That single observation captured the war's quietest turning point. The age of forged war had ended. The age of manufactured imagination had begun. As Allied convoys rolled westward, hauling crates of American equipment and spools of resin-coated wiring, the captured scientists stared at the discarded translucent shells on the ground and recognized them for what they were: the smallest, lightest proof that they had lost to an enemy who could reinvent the substance of war itself. The aftermath of that revelation would reshape, not just industry but identity, for the plastic bullet had announced the one conquest that outlasted empires: the mind's victory over matter. When Germany collapsed in May 1945, the victors divided not only its territory, but its knowledge. Allied scientific recovery teams raided laboratories across the Reich, collecting data, blueprints, and samples of everything from jet turbines to explosives. What they sought most urgently was evidence of material innovation, a subject that America, with its recent polymer triumphs, now understood as the key to the next century. Inside airfields and chemistry plants from Leipzig to Merseburg, American and British inspectors uncovered warehouses of steel, brass, and copper reserves, proof that Nazi Germany had remained chemically conservative until the end. In contrast, trunks of captured Allied ordnance told a radically different story. Translucent fragments of polymer shell casings, radar housings molded from resin, plexiglass aircraft domes, synthetic rubbers, and nylon insulation were cataloged by stunned German chemists assisting the occupation forces. To the engineers newly demobilized from Hitler's armaments ministry, those finds cut deeper than defeat. They realized that while Germany's scientists had labored to perfect metallurgy, their enemies had moved beyond it. The discovery humiliated an entire generation educated to believe progress existed only in alloys. Chemist Ernst Ziegler, interrogated near Frankfurt, admitted bluntly to his captors, "We chased hardness when we should have chased flexibility." Meanwhile, American laboratories were already redirecting wartime polymer research toward civilian prosperity. DuPont, Dow, and Monsanto absorbed data from the Army's lightweight ammunition project and the Navy's plastics program. Injection molding, the same process that had stunned Keller and Ziegler in that bunker near Remagen, became the backbone of post-war American manufacturing. Unclassified in 1946, the ordnance report circulated through industry with little fanfare. Its title was dry: Feasibility of Non-Metallic Cartridge Design. Yet inside, it contained lessons powerful enough to launch a peacetime revolution. Engineers adapted the casing's heat-resistant formulas into consumer goods: telephones, electrical plugs, dinnerware, even the dashboards of the cars that would soon fill every U.S. highway. The effect on global economics mirrored the transformation on the battlefield. The same factories that molded rifle ammunition began producing the piece: washing machines, radio shells, children's toys. Chemistry had stepped permanently into the realm once held by metallurgy. The United States had shown that an army of chemists could change the structure of civilization as surely as an army of soldiers could change borders. For Germany, the reckoning came slowly. In 1947 and 1948, during Allied denazification reviews, scientists from IG Farben, once the empire of European chemicals, stood before tribunal panels describing their wartime projects. They spoke of synthetic fuel, artificial rubber, and nerve agents, but almost none admitted to forward-looking polymer design. They had made weapons that killed efficiently. They had not imagined materials that could win the future. American interrogators occasionally placed translucent cartridge samples on the table during questioning, not as evidence, but as symbol. More than one German engineer lifted the molded fragment, turned it between his fingers, and fell silent. The material that had seemed a curiosity in 1945 was quickly transforming into the DNA of Reconstruction, used in aircraft interiors, medicine, and architecture. By 1950, every industrial nation was trying to replicate what the Americans had proven: mass production through chemistry. The patent floodgates opened: polyethylene fibers, polystyrene cases, acrylics, and vinyl. From Manhattan's skyscrapers to Berlin's rebuilding suburbs, a new material world shimmered under post-war sunlight. Ordinary Germans found plastic in every imported product stamped "Made in USA," and many recognized the echo of those impossible bullets found in 1945. The silent weapon of adaptation had outlived the loud ones. What began as a wartime experiment now molded the peacetime landscape, bridging destruction and domestic comfort. The same substance that once fed rifles would soon feed prosperity. Yet buried beneath progress remained a quieter acknowledgement. Chemistry's miracle had been born out of fear, necessity, and rivalry. Without the desperation of war, the modern world of plastics might have arrived decades later, or never at all. This uneasy origin gave post-war scientists pause, reminding them that every innovation carries within it the memory of its making. By the dawn of the 1950s, German industry started its own polymer renaissance, re-employing chemists who had survived the war and studying Allied patents line by line. Their nation rebuilt itself with the very lessons it had underestimated. The first West German plastics exhibition in Dusseldorf displayed molded casings under a modest sign reading, "From need, invention." It could have been engraved on every fragment left behind by the Americans. By the mid-1950s, the shock of Germany's collapse had shifted into introspection. In the ruins, a new industrial class emerged: men and women who had lost faith in the infallibility of steel and rediscovered humility in chemistry's infinite flexibility. Universities reopened laboratories once devoted to metallurgy and renamed them institutes for polymer science. Captured Allied documents became teaching tools. Lines from Frankfurt Arsenal's wartime reports, once stamped secret, were translated into German and read aloud to students who had grown up amid rubble. The irony wasn't lost on anyone. The next generation of German plastics engineers was learning from the very ammunition that had symbolized defeat. Across the Atlantic, the United States had already moved far beyond military needs. The factories that once poured phenolic resin into cartridge molds were now producing consumer miracles for a world hungry for comfort after decades of austerity. Nylon stockings replaced parachute cord. Polystyrene trays replaced metal mess kits. Lucite and plexiglass, once used for bomber canopies, now framed shop windows and neon signs in post-war cities. A material born from wartime improvisation became the texture of peace. The plastic age had begun, and its origins lay in the exact chemistry that wartime Germany had dismissed as trivial. For historians and scientists reflecting decades later, the so-called plastic bullet project represented a fork in technological evolution. Germany's industrial mind had pursued the harder path: stronger turbines, denser armor, higher pressures, believing perfection lay in hardness. The American mind had pursued adaptability: make it lighter, faster, reproducible. The lesson extended far beyond ammunition. In Cold War laboratories, soon sprouting on both sides of the Iron Curtain, engineers applied the same principle to missiles, aircraft skins, and circuits: function through flexibility. In interviews conducted for Allied occupation archives in 1946, German researchers repeatedly described their astonishment at the speed of U.S. innovation. One physicist from the Ruhr's Aeronautical Institute admitted, "We thought of change as risk. They thought of change as inevitability." That line outlived him in textbooks on engineering ethics. Adaptation, once a slogan for wartime improvisation, became doctrine for global industry. By the 1960s, both nations, now NATO allies, had integrated plastic fabrication into nearly every field of manufacture. From machine enclosures to high-pressure tanks, engineers who had once faced each other across battlefields now exchanged studies at international conferences in Frankfurt and Cleveland, quietly acknowledging that their post-war prosperity rested on technologies born under fire. The deeper legacy, however, was philosophical. In Berlin, professors cited the resin cartridge experiment as a turning point in humankind's relationship with material certainty. Matter itself could be reinvented to suit ambition. That realization fueled both consumer dreams and existential dread. If chemistry could render metal obsolete, What moral anchor could restrain invention at all? The same laboratories that molded the first lightweight ammunition would, within a decade, invent plastic explosives. The same malleable genius looping from protection to peril once again. Journalists, who revisited the American Ordnance Archives in the 1970s, found yellowed memos referring to the project simply as a successful experiment, unnecessary after cessation of hostilities. They were startled to see that few of its participants had sought recognition. For them, the work was less about the material than the mindset, proof that in modern war, adaptability wins where force fails. Back in Germany, surviving engineers like Ernst Ziegler and his colleagues would spend their final years consulting for civilian companies, molding car dashboards, telephone casements, and hospital devices. They spent their careers surrounded by what had once seemed impossible material, produced daily and discarded casually. When asked about their first encounter with Allied polymer ammunition, Ziegler reportedly smiled faintly. "We called them toys. They turned out to be the tools of tomorrow." That nuanced humility defined post-war technological culture on both sides of the Atlantic. The arms race had metamorphosed into a race for convenience, for abundance, for transformation itself. In countless homes across the world, the quiet echo of that wartime discovery persisted, in the touch of every molded surface, in every transparent screen, in every modern invention that measured success not by strength but by possibility. From the rubble of 1945 had emerged a civilization built, quite literally, from the most underestimated substance imaginable. The engineers who once dismissed plastic as weakness now lived inside a world it created. And in that ordinary miracle lay the final measure of their astonishment, an afterword to war written not in metal or fire, but in the flexible clarity of man-made lightness. The story's reflection was no longer about defeat or victory, but about the question that outlasted both. When humanity learns to reshape the very materials of existence, can it ever truly control what it creates? When the engineers of 1945 held that translucent cartridge in their hands, they weren't merely handling a new material, they were touching the threshold of a new era. For centuries, war had been forged in metal and sweat. Now it could be poured, molded, and replicated out of the chemistry lab. The bullet that had once shocked German science signaled humanity's quiet migration from the age of iron to the age of invention itself. The great paradox of that discovery was its intimacy. A small, almost weightless shell containing the moral weight of an entire century. Out of necessity, America had turned to polymers to survive shortages, yet in solving a wartime problem it had created the blueprint for modern life. Plastics would later clothe the world, carry its food, sheath its wires, and choke its oceans. Every triumph in lightness would cast a shadow of permanence. For the defeated engineers, the plastic bullet became a symbol of humility. For the victors, it was proof that creativity, not tradition, defines power. What they both learned is that adaptation, the willingness to reinvent matter, matters more than any arsenal. In the silence that followed war, laboratories replaced bomb plants, and the same chemistry that once shaped bullets began shaping the future. Beneath every molded object somewhere lingers the echo of that discovery. The moment a substance once dismissed as imitation taught humanity how to reimagine itself, for better and for worse. From that single cartridge onward, the story of progress could no longer be measured in tons of steel, but in the courage to believe that even the softest things can change the course of history.